Hi, Ward.
Oh, hi, Ed.
I
How
don't
are
think
you?
this is what anyone was expecting. Least of all me.
I think lightning talks, no one knows what they're expecting.
It's true. It's true.
And yeah, I think we're just kind of going to make it up again, as we always do.
I think well, like I was saying to you, I haven't watched these. So let's get to
Well,
it. We'll have some live
let me
reactions.
start with a couple quick things,
Okay.
right? So, first off, sorry to the crowd out there because I didn't tell everyone whether or not their talk was not accepted. We kind of did a rolling acceptance and submissions like we do, and like thanks you all for submitting stuff.
Uh,
And like, you
how are
know,
you doing
thanks
that,
Ed for trying
Ward?
to stitch all this stuff together at the last second.
How are you doing that?
And
I'm
so
so confused.
we tried to stitch a bunch of things together in the last minute here. And one of them was I was going to try and send you an OBS stream
Yeah, you were.
so we could do it live. And like we were going to send you like all kinds of stuff via Zoom. And so there's only one person, Zachary, that wants to actually do it live, and he's gonna go first.
Brave. So let's
So
see what
let's let him
happens.
do it.
All right. I should probably find the mute button because otherwise this is
Oh
going to be
yeah.
very bad. All right, here we go.
Hey, folks. Super excited to be here. And like Word was saying, I couldn't come to Demuxed and not talk to you live. I have too much fun with it. Plus, I don't have time to make slides right now. But super excited to be here. And just because I am the video nerd I am, above me, you'll see my local time NTP synced. And so we can really figure out what the latency of this low latency stream is. But that's not what I'm here to talk to you about. I'm here actually to tell you a story. And to tell you the story, I got to rewind back to 2019, which feels like so much more than 2 years ago. And Demuxed, actually 2019, after that conference, which had great talks, it had great socialization, had a little too much to drink. But we all got together and we were talking about low latency streaming. And we actually got together at Apple headquarters to talk about the future of low latency streaming. With and try and find a way to bridge what the Dash community was doing, what the HLS community was doing, because they were actually moving in very opposite directions. And there's a huge group of folks from the video dev community and just the industry overall that got together to have this discussion and hash it out, which was great. And at the end of that, we had this amazing revelation. Like we were realizing the reality of CMAF. We were bringing things together. Irrespective of how you're addressing it, you could make the media once and stream it. And after that, all of us thought, what if we could do this for everything, right? What if we could bring all of our formats together and make it so that you make media once, you stream it however you want to stream it, and it just works. And so that's where we got together and pitched an idea, to the CTA group that very, very nicely let us participate. And we said, okay, we want to do two things. We want to say, I've got CMAF, I've got Dash, I've got HLS. What can I do to make it so the CMAF is usable in all of these things? And on top of that, how can I go ahead and convert between HLS and Dash? These are big topics. And I want to make sure this is actually usable in the industry. And so we formed a group called the Dash HLS Interoperability Group. And we set out to find a way to bring this all together. And it took over a year, but luckily we were all, stuck in our houses. And so we had a lot of time to write and think. At the end of it, we actually put together a lot of these things. And so we've got an initial draft out, our initial document out, which brings together Dash and HLS through CMAF. And we'll be presenting about it more in a few weeks and hopefully Mile High. But I'll drop some links to it. If you're interested in producing media once and using it in Dash and HLS, we want to have you join and help us out because this is it's just the first step, and we want to bring the industry together.
Thank you. And now I get my CPU back from running Zoom and everything all at once. But I have to say, it seems like the theme is overlays. Is it the Final Frontier? Let's see what Tiago has to say about it.
Hey Demuxed, Thiago Teixeira here, and my talk is on streaming video to the final frontier. I work for Brightcove. I'm here in the Boston office for what it feels like forever, and opinions and materials are my own. And first, I'd like to thank the organizers for taking my talk. I think it falls into the crazy ideas category. And so the motivation is, how do we get content from outer space back to Earth? So what kind of protocols do we use? Is rate adaptation even possible? And while I'm not going, I don't have time to answer all the questions and do like a lengthy presentation. I'm just trying to kind of bootstrap video research on this topic. So bear with me. When we're talking about outer space, it's really a new paradigm. So if you take Mars, for example, round trip time between Earth and Mars varies from 6 minutes when the two planets are close together, all the way up to 40 minutes plus. So it's clear that current internet protocols don't work or are not suitable for this kind of environment. And there's also the issue of low data rates. So you can see that from rover to Earth is like 32 kilobits per second. Things can get a little bit better if you go through the orbiter. But however, there is hope. So NASA is testing a laser communication between Earth and Moon and the Moon that can reach 600 megabits per second. So things might get better in the near future. And to answer some of the questions, we use delay tolerant networking, or DTN. And so we add a bundle protocol to the network stack. And with that, what that does is turn nodes into custodians, meaning that once a node receives a bundle, they store and then they forward the bundle. So if there's any issue between the communication of two nodes, a node can just retransmit the bundle and things. There are more details to that. But NASA and other space agencies' implementation of this bundle protocol is called Interplanetary Overlay Network, or ION. And so I linked a couple resources that I highly encourage you to visit. There are images that you can play around with. There's an internet research task force. So I hope you enjoyed the talk, and I hope to see some talks about this topic in maybe Demuxed or other video conferences in the near future. Thank you.
Well, thank you. And now there's a lot of talk going on about latency. So let's hear another talk about latency at scale.
Hello everyone, I hope all of you are doing safe. I'm Kshitij Gupta, CEO of 100ms, where we are building live audio video infrastructure for the developers. Today I'll be talking about building clubhouse style audio rooms, which should not crash when Elon Musk joins. Let us first define what an audio room is. An audio room is similar to a panel discussion happening on the stage and people listening to them in an auditorium. Let's map this into a digital world. There will be 5 to 10 speakers who can talk to each other in the most natural way. For a natural conversation, the latency is the highest priority. I would say the ideal latency would be less than 250 milliseconds. There could be an audience size of 100,000 or even a million people who can listen to speakers at sub-second latency. In this case, the listener experience takes higher priority than latency. That means it's okay to go higher on latency sometimes, but the glitch-free audio must take higher priority. At 100ms, we have been trying following approaches to solve this. The classic approach is using WebRTC plus SFU, which stands for Selective Forwarding Unit. In this approach, there is a single conferencing room. Both listeners as well as speakers are connected to the same room. Speakers are uploading their audio stream and downloading audio of all the other speakers. Listeners are not uploading anything, but downloading the audio of all the speakers. This particular approach scales well for speakers, but not for listeners. As you can see, the number of streams to be downloaded for listeners, when the listener count is 100,000, and even with 4 speakers, it becomes 400,000. Beyond the scaling complexities, the problem is that listener and speaker are treated equally. Listeners get audio at similar latency of speakers, but suffer with degradation upon packet loss or other network instabilities. Let us now look at an alternative approach. In this approach, we are using WebRTC plus a combination of streaming protocols like HLS and Dash. In this architecture, the speakers are on WebRTC stack. The audio of all the speakers is then merged into a single stream. It is encoded via a live encoder and then streamed to listeners over HLS or Dash via a CDN. The listener experience scales very well because of the use of CDNs here. However, the latency in HLS Dash, even in the best implementations, become 4 to 5 seconds. And if you're using an older phone model, it can even go up to 30 seconds. Let's now come to the approach we finally used involving WebRTC plus WebSockets. In this approach, we are trying to reuse an existing component in the conferencing stack. In our implementation, WebSockets are already present, which are used for signaling layer and the chat. We use the same infrastructure to pipe back the mixed audio of speakers to the listeners. And since we have already made our WebSocket infrastructure horizontally scalable, this gives us best of both worlds, where we are able to give a listener experience which scales as well as does not suffer from packet loss issues of WebRTC. Thanks for listening.
And I'm back with Ed. Oh, hi, Ed. Welcome back. Are you wondering how I'm doing all these overlays?
A little bit, yeah.
Yeah, well, I'm going to tell you one thing. It's not headless Chrome.
Oh, okay. Well, that's unfortunate.
The next talk is about headless Chrome, so let's cut to that.
All right, let's go.
Hey there, I'm Paul. I'm one of the co-founders of Stream Club. We build software to make it easier to go live from your browser. Today I'm talking about some driver nightmares I had. I was trying to configure my headless Chrome to work with a GPU on Linux in the cloud. It was a nightmare. And I saw a lot of really great headless Chrome talks this week, and I wanted to share this little story I had about how I got it working and hopefully how you can get it working too. So first of all, headless Chrome is great. We don't have to talk about too much, but WebRTC support, it's super flexible. You can write code once, run it in 2 places, and there's a lot of developers, so we love that. It has some failures though. It's resource intensive. There's a lot of undocumented gotchas in the form of like Chrome flags and drivers you might need. It's hard to debug and there's a slow startup time, so you have to make sure you're smart about how you open and close the browser. But we're going to focus on the performance side here. There's a couple ways we do. If you want to use a GPU, there's probably a couple of use cases you should really care about. Ours involves a canvas. Really, anytime you're using linear algebra, if you start doing that pretty comprehensively, you may run out of CPU headroom. If you have a lot of WebRTC participants, you might get advantage of a hardware video decoder, which GPUs often have, especially NVIDIA ones. Or if you're doing stuff like TensorFlow.js or 3D graphics, start thinking about a GPU could really lift up your headless Chrome usage. So this will be looking for this Chrome GPU is kind of our guide to see if Chrome is configured correctly. So as you would be setting this up, you'd be constantly checking this page to make sure that we have all green and we're all hardware accelerated. How we're going to do it is we're going to use containers to make sure that we can pin the resources we want to use. We don't want to let Chrome use as many as it can. Joel from Browserless.io says that Chrome can really get good at taking as much resources as it can, and I've noticed that as well. So we keep it all in a container. It also makes it easier to replicate what we do and set stuff up the same each time. We'll use NVIDIA GPUs. They have the best driver support for headless Chrome on Linux, at least from what I've seen, and it's the only way I've gotten this working. There's some Chrome flags that we'll share that are important to get this set up so you have the right settings and the right decoder set. And to be honest, this took a lot of trial and error. So, this is going to be a tricky process, but we made it way easier because I'm actually going to give away the Docker image that has this all working. It's called Stream Video Image. It's headless Chrome with NVIDIA GPUs, MIT license, and I put in some samples of Puppeteer code with all the flags you need. Stream.club/GPU. Check it out. I hope people use it. It's been really helpful for us. If you need this image, you might want to check out our SDK. We're making a in-browser live streaming SDK that gives you WebRTC hosting, state syncing, media assets. Basically, all the infrastructure stuff is abstracted, and you just drop in the SDK, and we handle the rest. It's really cool. You can check it out. Stream.club SDK. Just looking for feedback too. If you're interested, love to chat about it. It's been really fun to build. And yeah, thank you for watching this talk. Thank you, Mux, for hosting all this. We love Mux. And check me out on Twitter. It's PK_IV, or email me, paul@stream.club.
Thank you, Paul. I think the only thing more prolific at Demuxed conferences is probably talks about encoding. So let's get a talk about encoding. Take it away.
Okay, welcome. Let's get started because this is a lightning talk and we have to go fast. I wanted to explain to you the 2 most common questions that I get with HESP. High efficiency streaming protocol, and you might already be wondering, why did you actually do HESP? We have all kinds of cool stuff like smooth. Well, latency, something you can do with a lot less of. Loading spinners, high startup times, not really things that viewers are tolerant about. They really expect top-notch quality, and you need to keep that finance guy happy. Scaling out these kind of things usually costs a lot of money. HSP was actually focused on all of these aspects. If you want more information, the specification is available on the IETF website, and there is the HSP Alliance website with a ton more useful information. Once you start digging into it, you'll notice that we actually use two streams with HSP. You have the initialization feed and the continuation feed. Initialization feed, it is basically a decoder config, PSSH boxes, and a first video frame. Continuation feed, basically that video frame from the initialization feed gets injected in there, but the continuation feed is your normal HLS or Epic Dash feed. This has a very good advantage. With that initialization feed, you can start up extremely fast. A few hundred milliseconds actually does the trick. It means you can reduce your buffer size, reduce your latency, and it gives you an extremely smooth viewer experience because your ABR can switch extremely fast. All of this done over HTTP-based CDNs, so that finance guy, he's happy. Now, first question I usually get, can you just do this? Can you just inject any random keyframe into a continuation stream? The University of Ghent has actually done a ton of research on this. They've been checking out H.264, H.265, they're looking into H.266 as well. If you look at perceptual quality scores, a VMAF difference of 6 points becomes perceptually noticeable. We are well below that. So very interesting approach, check out their work, and then we can keep going with that. Second question that we get usually, you want to keep that finance guy happy, but you're doing a lot more encoding jobs. Twice the amount, because you have initialization streams and continuation streams. That's absolutely right. You have about 60 to 70% extra encode, but you can be smart about this. You can actually bring down that number. You can make it 20%, you can make it 15%, you can make it 3% without real impact on user experience. So that's very, very interesting. Now this is a lightning talk. If you want more information on all of this, just reach out to me. But well, I can't go over my 3 minutes because if I do that, then they will simply just...
Oh, they did. They covered that. That was some serious decoding artifacts. So let's go to a talk on decoding.
Hi, I'm Thomas Dady, and I'm here to talk to you about Ravi's literal edge cases. And by that I mean the edges of the video. It all started with this bug report of a gray line on the bottom of an AVIF file encoded with Ravi. Why does this happen? Well, as much as we'd like, video and images are not an infinite plane of pixels, and handling edges is tricky and easy to get wrong. Video games are often culprits, and if you've never noticed any game getting this wrong on its textures, then sorry, because I've ruined every future gaming session for you. The edges are only a few pixels, but they're especially important for cases where the image or video needs to blend into other elements, such as CSS elements on the page, or is tiled with other videos. In Ravi's case, there are actually two things to fix. In AV1, all pictures are logically multiples of 64 by 64 or 128 by 128 superblocks, with cropping applied to those. When encoding, we made this error of considering pixels that were out of the visible frame for our distortion calculations. This resulted in making weird coding decisions. Fixing this gave us a healthy 0.2% improvement. Not big, but standards body battles have been fought over less. The second problem is how we transform and quantize edge blocks. Sharp lines in transform-based codecs can cause ringing at low bit rates, as anyone who's ever seen a JPEG can attest. The edges of the image are no different than an edge anywhere else in the image, and if not specially handled, will still cause ringing. There are a pile of solutions out there for this, such as extending the pixels of the edge of the input frame to the superblock boundary. David Michael Barr and I tried several methods, and currently settled on using a slightly fancier low-pass edge extension technique. He also wrote a nifty edge metric showing the improvement of our chosen technique near the edge. I'd also like to emphasize this is not a new problem. MozJPEG implemented a similar solution, and Tim Terraberry has a paper comparing several different methods. There's no right answer, but there are definitely some wrong ones. Thank you for your time.
No, I messed up, Ed.
Uh-oh.
We should probably just replace me with AI.
I mean, I guess.
So, let's listen to a talk about AI. I got that one right.
Good afternoon, everyone. My name is Solomon Shaw. I am an AI researcher and software engineer here at Stainless AI. And today I'll be describing an algorithm for automatically and intelligently reformatting videos from widescreen to vertical viewing formats, such as the ones you see on TikTok, Snapchat, or YouTube Shorts. So more specifically, given a widescreen video, the goal would be to go from widescreen aspect ratio to a smartphone aspect ratio by intelligently cropping certain regions selected by our AI-powered algorithm. And on the screen, you can see examples of what that looks like. So before we get started, the first thing you'll need to do is select the type of content you want to build the algorithm for. We decided to go with soccer videos, but you can choose anything, such as dance videos, movie clips, and so on. So once you have one type of content, extending that onto another type of content involves the same process. So step one for the algorithm is to build an object detection model for the most interesting objects. So you'd identify the objects that are most relevant to the content that you chose and train a model to detect those objects in every frame. So for soccer, these would be things such as the ball, the players, the goal, etc. The model will give you a bunch of bounding boxes for all the objects it has found, and you would want to compute the center of all those bounding boxes, giving you a bunch of XY positions. Next, step two is to average all the XY positions you found in step one. And you'll probably need to do a weighted average where each type of object gets a different amount of weight depending on how important they are to the scene. Step three is to smooth the position of this average as you move from one frame to the next. And you can pick your favorite smoothing algorithm for this task. Now, our parameters like the object weights and how much to smooth, etc., may need to be different based on the type of scene you're looking at. So to accommodate this for step four, you'll want to define parameter sets that work best for different type of scenes. And then for step five, build a scene classification model to help you choose the appropriate parameter set. And then finally, for step six, you want to build a transition detection model that detects cuts or fades in your video so that you only need to run the scene classifier whenever there's a new scene. And then that's it. Once you have all those pieces together, the final step is to put that into a pipeline and crop around the average position that your algorithm has detected. So if you have any questions or comments about the algorithm, you can reach us at info@stainless.ai. And with that, thanks for listening.
Well, I think there are some serious questions right now about the quality of vertical video. So let's listen to a talk about quality.
Hello, Demuxed. My name is Chris Kulbakis. It's great to be here. I'm a video engineer at CBC Radio Canada, building TV and radio streaming and monitoring workflows. I'm also the lead for SVA's Video Quality Tags project. The project is a collaborative effort. Its core contribution group is represented by the logos above. So what are video quality tags? They are video streaming QoS and QoE metrics. They leverage multiple sources of data, including CMCD keys from the players and log data from the CDNs. They can be used by CDN operators for efficient log parsing, session-level correlation, network performance, and viewer experience measurement. They support different use cases, including issue detection, diagnostics, and optimization. To level set, CMCD enables players to send QoS and QoE data to CDN logs. This data is sent with every object request using HTTP headers or query arguments. Metrics are computed from the player perspective and include player buffer levels, buffer underruns, player measured throughput, etc. Although CMCD provides some QoS and QoE data, the player side can provide additional visibility. So the idea is to leverage CMCD by proposing additional CMCD keys and key-derived metrics, proving them out in an SVA POC, and publishing an SVA tech doc proposing the new CMCD keys, derived metrics, and associated use cases. The goal is to augment CMCD with new keys and thereby to enable additional diagnostic and optimization use cases. In phase one of the POC, the team is implementing 3 use cases: distributed request tracing, already presented by Josh in yesterday's Demuxed talk, manifest composition and utilization metrics, as well as network delivery pacing metrics. Distributed request tracing focuses on how streaming sessions utilize the underlying CDN infra. Can we establish a request response chain and find bottlenecks for a given session? Can we decompose the session into parent and child spans? Here we use the existing session ID key and a newly proposed request ID key The team is investigating using a tree structure to represent a session where vertices are the nodes making object requests and edges are the individual requests. Manifest composition and utilization looks at how players use their manifest during content consumption. 3 new CMCD keys are proposed. Obtained manifest index tells us how many representations are present in the manifest. Playable manifest index tells us how many of these representations players can actually play. Current manifest index tells us which manifest is currently being played. These proposed keys are then used as building blocks to derive metrics such as manifest utilization per session. MUS allows us to quantify manifest utilization over session lifetime. In the following example, the first session is now able to stay on the top bitrate and shows MUS of 50%. The second session stays on the top bitrate and has MUS approaching 100%. The third use case is delivery pacing. Its purpose is to check if CDN is keeping up with player capability and demand. Using data from CDN logs and existing CMCD keys, different CDN to play delivery pacing metrics are computed, including measured throughput pace, requested throughput pace, top rendition pace.
Hi, Ward. People
Wow, what was that?
People really shouldn't go over, should they?
Don't do it. Don't do it.
Don't do it. Don't do it. So who's up next?
I have to keep sparking the flames here of, little trolling, little arguing. I think the greatest argument in the video community right now is Dash or HLS.
Hi, I'm Garrett. I work at Brightcove, where I help develop VideoJS's main playback engine, VideoJS HTTP streaming, which is a lot to say, so we call it VHS. VHS was originally an HLS playback engine, but we managed to make it play Dash too. VOD worked great. Live gets the neutral face emoji. As a totally unrelated aside, there's an HLS Dash interop spec that we're going to completely ignore. For now, I'll give the reason as we're lacking CMAF segments. Here are a couple of HLS and Dash VOD playlists. There's no way I had enough ink for full Dash manifests, so this is all we're getting. VOD is easy. You have a list of segments and you put them one after the other. So let's make them live. Now they're live. HLS segments are ordered by index, so for live, we get 2 numbers in this manifest. And don't be alarmed, but my hands are about to enter the screen. Those 2 numbers are media sequence and discontinuity sequence. Media sequence tells us the first segment's index in the overall stream, and discontinuity sequence tells us how many discontinuities are now behind us. In order to get live Dash playing in an HLS engine, we need those 2 numbers. The start of a stream is easy. Everything can be 0 for Dash, but let's refresh them. Periods in Dash are discontinuities in HLS, so to get the sequence number, we need to keep track of the periods we've seen, and for that, we need a way to tell them apart from each other. In the 2019 Dash spec, period ID is mandatory for dynamic playlists. If you can get away with using the 2019 spec, use that. We can't, so period ID is out. Period start, though, can be used, and it can't change as of Dash interop 412. So let's map period starts to discontinuity sequence numbers. And that's discontinuity sequence. Just increment by 1 each time you see a new period, and keep those mappings stored somewhere safe. Now we need media sequence. First, don't try to determine the media sequence by matching segment URLs. Content can repeat, and segment URLs can change. I learned those the hard way. But we can rely on segment presentation times. In this example, we'll have a match for the first segment at presentation time 2 with the last manifest. But don't rely on segment matching alone. Representations can appear and disappear on any new period. As another challenge, you can have a refresh like this. Here, there's no segment to match on. So what can you do? First, try to do what we just discussed and match on representation and segment presentation time. Second, if there's a representation match but no segment match, then it's either a discontinuity or a gap where we missed content. If it's a new period, it's a discontinuity anyway. If it's an old period, then it's playback engine's choice between adding a discontinuity or handling a potential gap. Either way, your media sequence is just 1 greater than the index of the last segment in the prior manifest. Third, and last, if there's no previous representation, just give the first segment a media sequence of 0. Now we have our discontinuity and media sequence numbers, and VHS can play live Dash much better. Thank you.
Thank you. Well, I think the only thing that we can agree on as a community is that we actually all love captions. So what's Lightning Talks without some captions? Take it away, Ed.
Hey Demuxed, GStreamer and AWS transcribe in 3 minutes, so let's go. Now video is hard, that's why we're all here. But I would argue that closed captions can be hard as well. The backstory to this is a few years ago, my company decided to rewrite part of our application using an open source media framework. we chose GStreamer. But we quickly realized that closed caption support was rough. This wasn't unique to GStreamer. Most media frameworks at the time treated closed captions as an afterthought, though that has been getting better. So we decided we can do this. So this is what a GStreamer command looks like. Go look up the syntax if you need it. So first problem is we need to treat captions as streams. Most media frameworks like FFmpeg GStreamer tack the captions onto the video itself, but we want to work with it as streams so we can do cool stuff with it. So CC Extractor allows us to take captions out of video streams and treat them as their own streams. Next, we need to do some conversion on those captions. If your captions come from H.264 and you need to get them out broadcast as a closed caption data packet, we need to do some conversion. CC Converter can do those conversions for us, along with common broadcast frame rate conversions. Finally, a lot of things need the captions recombined, like X264. So to recombine the captions, we use CC Combiner to take a caption stream and a video stream and recombine them. So that's cool. We've solved all the closed captioning problems in our app. What do we do next? At the time, AWS Transcribe was really becoming usable. So we decided to take the format that AWS Transcribe gives us and try to make some subtitles or captions out of it. So AWS Transcribe Parse is a GStreamer element that will take the format from AWS, and then we can turn it into time text and put it into an SRT encoder and get an SRT file out. But the formatting is horrible. You basically get one word per line because that's what AWS gives you. So enter in text wrap, which is an element that can take that closed caption, the time text stream and format it into a certain amount of columns and lines. Then we can pipe it into SRT encode and get it to the file, but it's still not closed captions. Finally, we have time text to CEA 608, which can actually take the time text stream and convert it into an encoded closed caption stream. And then we can put it into SCC encoder to get a common closed caption sidecar file. There is a lot more that GStreamer can do, including live support and some VTT support. So please check it out, because right now, all open source, you can subtitle and caption your content with what's available in GStreamer. Thanks.
Hey,
Hi,
Ed,
Board. What's up?
did you know that there are formats in captions?
To my great chagrin, yes.
Well, I think we have a way to convert between them. So let's
I
hear
also saw
what
that.
Pierre has to say about
and
that.
you need to go to jail.
Hi everyone, I'm Pierre and welcome to this lightning talk. Some of you might know me from my other lives in W3C or SMT. Today I'm wearing my hat as maintainer of TTConv, which is an open source project for the conversion between subtitle and caption formats. Subtitles and caption, that's the text that's overlaid over video to provide accessibility and translation. Might not come as a complete surprise that just like audio and video, humans have been extremely prolific in creating file formats for subtitles and caption distribution. One of the simplest that I'm sure all of you might have seen is SRT, subrip, which is just a plain text file that contains a sequence of subtitles. Each subtitle has a start and end time and contains plain text. Actually, it's not exactly accurate. It can also contain tags that specify font style and color. WebVTT is basically like SRT, but with the string WebVTT on top and some CSS-like styling. It's a W3C recommendation. TTML, the time text markup language, another W3C recommendation. So this is an XML file. It's kind of like XHTML, but not really. SCC is a way to carry CTA 608 caption in plain text file. CTA 608, which used to be called CEA 608 before the CA changed its name, is a standard for traditional US broadcast. The 608 stream is actually not a sequence of subtitles, but instead a sequence of drawing instructions at 60 fields per second. And finally, EBU-STL, which is a format specified by the European Broadcasting Union. It's a binary file and contains a sequence of individual subtitles. Of course, there are many, many more formats, some of which, like Lambda Cap, are particularly popular in Japan. SimTST 428.7 is used in cinema, and Substation Alpha, which is used in FFmpeg, among other places. Of course, conversion from each of these formats to any other of these formats is very difficult. There's many of them, and every time you think that a particular conversion is not useful, somebody will ask for it. TTConv, which is an open source library and command line application written in Python. It tackles that problem by defining a bunch of readers, which converts input subtitle files into an internal model, and a bunch of writers that convert this internal model into a desired output format. The internal model is based on TTML, since TTML is a pretty flexible data model. Very quickly, so this is hosted on GitHub. Very quick example here. This demo, an SCC file is converted to a TTML file. This uses a web app that's hosted at ttconf.sandflow.com, just a demo app. And then something to note is that the roll-up effect comment to 608 caption is preserved in a conversion. And what's in the future? Well, support for more format. Thank you very much.
There's a couple moments that just make me say, what?
How's it going?
Ed, I'm having that feeling right now. What is going on with your background?
I don't even know anymore.
Okay, I don't have it.
All right.
Take it away.
I can't turn it off until we leave.
Oh.
We should do this. We should do this. Because really this is starting to hurt my head.
Let's take it away to, this section of talks is the section that sometimes I can't explain, and we have to take the talks that are just different.
It's true. And I will say, this one is very topical.
Hi, I'm Brian Corner, and this is my lightning talk on Henry Street lights, or how to be one of those crazy Christmas lights people. Normally I work for Fox Corp, but today this is all about my Christmas lights. So we have one of those cool displays that you always see on YouTube where the lights are dancing and the music is playing and there's all kinds of RGB effects and stuff. Quick history, we've been doing this for about 11 years, and as you can see, our display has grown in size and color and complexity and certainly technologically over those 11 years. The first thing we have to do is program all of our songs. This takes us a very, very long time. You can download these already pre-programmed. We don't really like to do that. We like to create new songs every year, and we do this is our artistic expression, so we do it ourselves. Then we got to wire everything up. This process really starts right about now. It started back in July and August when everything went on sale and we could buy new things, but now we've got to get it all out on the yard. There's a basic light controller. There are 4 RGB controllers, 200 addressable RGB pixels, 8 RGB floodlights, an FM transmitter, a control computer, an amplifier, speakers, many, many strings of normal lights. And what's really important is our magic doorbell. So the idea being, you drive up in your car, you get out of your car, you push the magic doorbell, and all of a sudden the lights come alive. Everything starts, the music starts playing, and all the lights start dancing around. But then COVID-19 happened. We didn't really want people crowding around in the front yard, because they do that. And we wanted to make sure that everybody could stay socially distant and feel comfortable. So what did we do? We got ourselves a Raspberry Pi. We wired up the GPIO of the Raspberry Pi into the GPIO of the controllers. Then we created an AWS EC2 instance and created ourselves a website. Pull up in your car and you can decide which song you want. If you're within range and we feel like you can see the show, we send a message back to the Raspberry Pi. The Raspberry Pi activates the GPIO trigger for the song that you wanted, and you have your song. This is a bit of what the website looks like on a phone. And it's really neat in that we can do this socially distanced, but then we also can collect a whole lot of data about what people want to hear and what they want to see. And if you want to see more about these charts, let me know, because I could talk about them forever. Most importantly, what we do though is when you do request a song, we request a donation to the Oral Cancer Foundation. And last year in 2020, we raised $3,025. We hope to raise even more this year. Again, my 3 minutes are up. My name is Brian Corner. I'm the Crazy Christmas Light Guy. Any more information, see me in the Slack channel.
Hi, Ward.
Hey. So I clearly got lightning and lighting confused.
Yeah, me
I'm
too.
sorry.
It's okay. We're good.
Does Lady know the difference?
Lady can't spell. She can, however.
I'm sure Lady can fetch.
Can she?
Can she fetch?
I mean, like, she'll go get the ball and then, like, drop it 10 feet away and be like, I'll meet you halfway.
What if it was a flag?
I don't
Could
know.
she capture the flag?
Let's find out.
Okay.
I just wanted an awkward silence first.
Hi, I'm Mark, a senior engineer and all-round video nerd at Unified Streaming, and I want to talk a little bit about something we did earlier this year when NAB was cancelled, which is running a video streaming Capture the Flag challenge. So what is a Capture the Flag, or CTF? The idea comes from the InfoSec world. It's basically a competition where you solve challenges and find flags, which are usually text strings. This is generally done by exploiting bugs, finding vulnerabilities, and breaking into systems. So how can this be relevant for video? Well, there's a field called steganography, which is the art or practice of concealing messages inside other messages. So a few simple examples of how you could do this. You could put unreferenced data in an ISO-BMFF MDAT atom. You could use SCI messages or undefined null types in an H.264 stream. And you can do a lot with image manipulation or audio manipulation. For example, change a specific pixel in every frame and have that form a pattern. We decided not to do any of these. We figured they're way too complicated, both for us to put together and also for people to solve. So we set ourselves some limitations. Our target audience for this is basically video streaming engineers, people that know HLS and Dash, not necessarily experts in low-level details of encoding. It should be fun, and it should be like fairly simple and straightforward. It shouldn't take more than a couple of hours to complete. We don't want people spending weeks on this. And also it shouldn't require any specialized tools, so you can do the entire thing in just a browser. So what does that actually leave us with? We can hide things in HTTP headers, we can put things in manifest comments and optional fields. For example, in Dash, we made a supplemental property that uses our own scheme and put a message in it. You can use timed metadata like SCUDdy35. Just put a SCUDdy35 event with a specific message that is the flag. You can use subtitles. If you queue a subtitle 1 hour into a 5-minute video, it's never going to be displayed, but you can put your flag in there. You can also do stuff with DRM. So an AES 128 key, it's just 128 bits. That can be an ASCII text string that points to something else. So how did it actually go? We had about 30 players that submitted answers. The feedback generally was pretty positive. Everyone contacted us that said it was fun. We had a lot of fun ourselves putting it together, both thinking up these puzzles and making videos to use, including one that we filmed in a location people might recognize. We kind of want to do it again sometime. So yeah, please get in touch and let us know if this is something you find interesting, either to participate in or maybe to run your own. Thank you.
So that brings us to the end of our lightning talks, but we do have a little bit more to get into.
Yeah.
So
Did you see I put my RGB lights on for you?
Oh, you did. Oh,
Ed,
you did.
Did you see?
Yes.
Ed, you got to one up them. Turn the flashers back on.
I actually don't know if I can do
Is
this
that-
like without looking.
Is that not on like a button like everything else that you have over there?
There we go. I had to go find the right one.
Wow.
It is on a button. Everything's on a button.
Can I
for
slow
Al-
it down?
for
I think
Ed.
I can slow
Wow.
it down. There we go. That
is-
helped the encoder out. But Ward, Phil and I have some business
Yeah.
to attend to. So
Why don't
We're
you
gonna
guys tell everyone all about all the buttons you press and how we make this show work every year as is tradition?
we could do that. We could do that. Bye, Ward.
Get me out of here.
Up. Now I'm Ward, and you're still Phil.
Yep.
So
So close.
there we go.
Hey,
Awesome.
we did it. We did it.
So we were going to have a presentation, Phil, and then we didn't.
Yes, we were.
But do you know what we do
busy.
have?
Lights that change color,
I
apparently.
mean, yes, but we also have questions. We have many questions.
Go on, then.
The audience has given us many questions. But first, before we get to the questions, I did want to call out one thing in particular as a moment of silence for Ray, who has slower internet at his house than the moon. Sorry, dude. Anyway.
That is tragic.
First off, what's the biggest change from last year's setup and why? I didn't change anything, so a little bit. We'll talk about that. But
Good question. I guess there's more than one stream this year. That's probably the biggest thing, right? When you click between those three buttons, they're all HLS streams. There was only one HLS stream last year, so it was a low latency stream, which is fun and chaotic at times. Thank you for all the feedback on HLSJS's ABR algorithm. We'll definitely take a look at some of those. Yeah, it's probably the biggest change. The caption workflow is pretty different.
Oh, really? Is it? Interesting, because somebody asked, what do we use for closed captioning?
What do we use for closed captioning? So the captions originate at Redbee in London. So we send the feed from Ed back to London, and we inject using a EEG Falcon encoder. Redbee do a combination of pre-prepared subtitles for as many of the talks as possible, and then also do live captioning. Hi guys, by the way, I realize you're now typing this as I say this, and inject it into the stream. And then the difference from last year is last year we were passing that through as 608 all the way through. This year we're extracting a 608 and pushing it into WebVTT.
Right on. Another one from Gareth, because Gareth's questions are the best ones. Do you have any fill insults on hotkey primed and ready? If not, why not? I don't, because I do my own stunts. But a real question from Sean: how are text overlays populated? Dynamic data sources manually entered. Do I actually still? I don't think I have the thing up, and I lied. Here we go. Nope. See, we're definitely doing this live.
Do a transition. Do it.
Yep, we're gonna go like that, and then I'm gonna go like this, and I'm gonna bring over the entire spreadsheet that has everything that we have done for the entire conference, and vMix, which is what we use because we like things that mostly work, pulls it straight from Google Sheets. It's great. This is how we're doing chat comments and stuff as well. How did we, Phil? Let's bring you back. Deal with internet issues during the remote conferences.
I mean, nothing super special. Number one, there's a couple of changeable signal paths. So if we do lose an internet connection, there are backup connections. There are actually backups, kind of full disaster recovery backups as well, that don't take any same infrastructure path as the mainstream does. You haven't seen any of those, touch wood. You won't see any of those, so that'll be nice. Obviously, we pre-record the talks, as you can see, for people who, we did have a couple of people who had intermittent internet issues during Q&A, which really justifies why we don't try and do everything live. It does create just that smoother experience.
Yeah, like the lightning talks were all premiered this morning by you and me.
They were. That was a horrid 40 minutes, wasn't it?
That was not great. Do you have backups, machines, and streams? I wanted to bring this up because, yes, we have backup streams. We do not have backup machines. Well, we technically do. We actually shipped one over, and then we'll give a peek behind the curtain. Didn't set it up. Ran out of time. But that's okay, because we also don't have a backup Ed. Jared is here, handling much of the commentation, the chat commentary. But yeah, if this went down, would have been fun. So we do it live. This is one that I'm curious about your answer, Phil. So I'm going to selfishly bring it up. What is the most broadcast grade (TM) piece of equipment you can't wait to replace with software?
For me, it is the EEG Falcon, I must admit. That is one of the most traditional, like the EEG Falcon is traditionally something you'd buy in a 1U rack and stick in a rack. And the version we have is like a cloud version, but it's like, you pay an annual subscription fee for this one copy of the software, and not kind of cloud native captioning workflow at all. So that's probably the most broadcast closed piece of kit that I'd love to replace with like a SaaS service.
Makes sense. And last question, because I have some fun answers to this one, but what's the worst mistake that happened that we didn't see? I mean, there's a happy little accidents meme with my face on it now, so I mean, like, mine are pretty clear.
I don't think we had any big ones. I opened a coffee a nice coffee on Monday night, and it just went everywhere in the London office, all over my laptop, all over desk. Like, I was kind of worried that I'd fried my laptop briefly. That was pretty bad. You didn't see that.
Sure.
That's probably the worst one we had. I don't think we had any really bad ones this year, did we?
I don't think we did, because we're excellent at this, Phil.
Touch wood. Touch wood.
Is that really wood, or is that just like...
No, genuinely, it's real wood. This bit's MDF, but this bit's real wood.
Just making sure. Anyway, we have to...
Ed, ask me one more thing. One more thing.
How
does the interpreted flow work? Ask me that.
That's true. I thought we'd... Yes. Yeah. How does the interpreted flow work?
Take a wild guess, Ed. It uses headless Chrome. Yeah, there we go. There's a shock. A really cool little experiment. So there's a headless browser running with capture of video output, and it's just a couple of WebRTC sessions composited on top of each other, captioned in web browser and streamed out. So we'll do a more in-depth talk on that at Headless Chrome Conf next year. Apparently.
We've already trademarked it. I have the domains, and maybe COVID will let us do that.
Yeah, that'd be good.
All right. So, Phil, I'd say this was a pleasure, but this was really just confusing.